So are you able to see my screen? Just a quick feedback from the participants.
Yes,
I
sir.
can see you. I can see you.
Yeah, so the thing is, while doing this lecture, so I want, I'll be asking in between, some questions. So in case if the students are willing to ask anything, they can ask me directly there so that we can solve the doubts. So today's topic is like,
So, Bharat, can you
generative,
make it
yeah,
full screen?
full screen. Okay, just a second. Full screen, I guess, because I have projected my iPad, so this is actually, I cannot make this screen big. It can
No,
be
it has
only
a view. It has a view option in the top.
just a
View
second.
option. Presentation option is there in the top of your screen.
More in this, just yeah, view option is there. Yeah, full
There you
screen.
can check.
Okay,
There
okay.
you can check.
So
Yeah, now
is
it
it
is
okay
big.
now?
Yeah, it's a
Yeah.
bigger size. Okay.
Okay, so so today what we will be discussing as far as the schedule is concerned, it's generative adversarial networks. So so whatever questions you have in between, you can ask directly so that we can discuss it. So today's discussion is about generative adversarial networks. So the thing is, let us start this and just a minute. Yeah. So for each of these terms which we have here. Sorry, the for each of the terms which we have here, like generative, adversarial, and networks. So let us discuss each of these three terms individually, and then we will have a clear understanding of what this generative adversarial network is all about. So I would request Professor Ghosh, can you please mute your mic because I think that's creating a
Sorry,
disturbance.
sorry,
Yeah,
sorry. I'll mute it. I'll
yeah,
mute it.
yeah, yeah. So first of the first term that comes in generative adversarial network is generative. So let's discuss this generative first, and then we will proceed further. So as far as the question that is coming in everyone's mind will be that what is generative modeling? So a generative modeling actually describes how a data set is generated in terms of the probabilistic model. So what we are doing here is we are actually setting up a probabilistic model from where we want to generate a new data set. So this is what generative models are all about. That is how to generate a data set from the probabilistic model. So what we have is like once we have this probabilistic model, turned up, then what we can do is by sampling from that model, from sampling from that probabilistic model, we will be able to generate the new data set. So generative modeling is more about coming up with the probability distribution so that once we have that probabilistic distribution, we can sample from that so that a new sample can come. We can sample it from the probability distribution. So we will discuss more about this in the coming slides, but this is the general overview of generative keyword, like what generative modeling is all about. Okay, so let me discuss first of all the discriminative modeling process, which is quite common. I think most of the audience must be aware of this, but let me discuss a bit of it here so that we can contrast it with generative modeling process. So here we have a discriminative modeling process where what we have is we have a training data, a set of training data. In this training data, let us say I am discussing, for example, a problem of cat versus dog image classification. So here we have cat images and here we have dog images, let us say. And then we have labels corresponding to the cat images as well as the dog images. So these labels are like, 0 corresponding to cat images and 1 corresponding to dog images. So what we are doing somewhere or the other is we are actually giving them, labels like cat is 0, dog is 1. So based on this type of training data set where we have labels attached with the cats and dog images, we are actually doing a training of a model which is over here. So this is a discriminative model which can be a neural network for like for example. So which maybe I think you will be getting aware of this in the coming lectures. But this discriminative model can take various forms. So for example, neural network as well as the convolutional neural networks and various others one. So what you are doing, you are actually training this discriminative model. And once this model is trained, now what you will do is you will take a test image, which is not in this data set. That test image can be of anything like cat or dog. But note that these cats and dog images which are taken in the test data set are not from this data set. So it has to be different. So once this test data set is there with you, so what you do is you feed this into the discriminative model and you get some prediction out. And the prediction is in terms of the probability. So for example, if this system, the discriminative model is giving you 0.83% output, 0.83 as an output, that means it is confident in, giving 83%, correct, like it is confident by 83% that the following image which you have fed here is a cat or a dog, depends upon which image you are feeding. So this is basically a typical discriminative model which actually everybody knows. So who is working in the area of machine learning and deep learning. So there is another modeling process which we call as generative modeling process. So let me invert the colors first so that this images will become proper. So let me do that first. So here if you see, this is basically a generative modeling process where you have some distinctions from compared to the discriminative modeling process. And what are they? Let us discuss that. So again, we have a training data set here also, as it was in the case of discriminative modeling. Same thing here also, we have a training data set. So but the difference is, in this type of training data set where we have, in which we are for this generative modeling process, the training data set will be of a particular kind of images. So for example, if I am working on cat images, let us say, for this particular scenario, so all this data set which I have here are basically cat images. So different type of cat images, all collected together, corresponds to the training data set. But note that here there is no labels attached to these cat images. But in the case of discriminative modeling, you had actually cat images and dog images, and label was also attached along with that. But here you only have a specific images, whether it's a cat or it's a dog, that depends. But in my example, I'm taking only cat images. And note that here there is no labels attached to it. So it's a completely label free training data set. So now what we are doing now is, we are using these images as the training images so that we can train our generative model, which we will be defining in our coming lecture. So what we will do is we will use this data set as a training for the training purpose to train the generative model. And now what we will do is, once this generative model is trained, then we will take a random noise vector. And this random noise vector will do what? It will project itself into the probability distribution which is formed in this generative model, and then it will generate the sample. And this generated sample will be a cat image. But the important point that is to be noted here in case of generative modeling is that all the cat images that you will get over here are completely different from the cat images that you have here in the training data set. So the images which are here are not present in this data set. They are completely new and completely distinct. So that's why the name generative comes, because you are generating some data which is actually not present in the training samples. So that's why this is an overall view of generative model. And to be precise, what exactly is happening is, these images, these cat images that you are having here, for example, let us say a cat image of size, let us say 28 cross 28. If you have a cat image of size 28 cross 28, then if you want to project it into a 784 dimension space where each of these coordinates are pixels of this image, so there will be 784 such dimensions. As you can see, 28 cross 28 will come out to be 784. So it will be 784 dimensions, and this particular cat image will be represented in the form of a small dot. So I think you will all agree with this, because in 784 dimension, this particular image, which is a 2D image, can be represented as a point. So what happens is, as you have this lot of training data set which is on the left side, all this data set will be clustered like this. It will be like this. So all of these cat images will be somewhere nearby each other, because their characteristics are somewhat similar in terms of the visual perception. So they will form a small cluster, something like this. So now what generative modeling is trying to do is, generative modeling is trying to form a probabilistic distribution of it. So it's trying to actually find the probability distribution of this particular samples. So what will happen is, I will be drawing a 2D contour of the probability distribution on this plane. So it can be something like this, it's a 2D footprint of the multidimensional probability on the two-dimensional plane I'm trying to show you here. So what happens is, generative model is trying to actually come up with this probability distribution, which is actually unknown to you, because you do not know what probability is actually governing these cat images, which is on the left side. So now when you put a random noise, which is here, this random noise, so that random noise will pick up, will be some point within this probability. So let us say it is this one. So this point is a new point in this probability distribution. So this corresponds to a new point. So for that, it will generate a new cat image. So that is basically the whole idea of generative modeling. And important point is that the seed point should not be too close to the already existing points, or it should not overlap onto the original points which we have here. So depending upon the distance of this point from all the other points which are in this probability distribution, the quality of the generative model is assessed. So this is basically a high level overview of what generative modeling is all about compared to the discriminative modeling. So once we have this, so you can see here, this is just a mathematical way of representing what I was telling, that discriminative modeling actually estimates the probability of y given x. So that is the probability of label y. That is, it will create a probability for label y given the observations x. So this is discriminative modeling, whereas the generative modeling actually estimates the probability distribution of x, where x is basically the number of cat images in our case. So this is basically the way of showing it. And just for a fun part, I will try to show you one small video which will it's a fun video, but somewhere or the other it will solidify your concepts in terms of what I have just told you. So let me show you that video here. So this is a commercial video from a car company. So I'll just show you here. You can see, and you will then realize that what kind of significance it has for this particular lecture. So are you able to see the video like properly? I just wanted to have a quick.
Yes, sir. Yes, sir.
Yeah, okay.
Yes, sir.
So can anyone tell what the significance this video has for this particular lecture? Can anyone answer this? Anyone? So the thing is, this video was trying to show you a person who was really interested in, buying that car, which is a branded car, but he was not able to do that because of because of the money constraint or so. So what he has done is, he cleverly, changed his own car, which was, some other model, into that particular car model. So it's what it is trying to do is, he is trying to, forge the system by creating a new car, which it is not. So keep this in mind, and maybe I will correlate this video with the concept that we will discuss in the generative adversarial networks. So here this person actually is acting as a generator who is trying to fool the system. So keep this in mind. So this person is actually trying to create a sample which actually, is not from the original car brand, but it's trying to mimic that by creating a artificial, sample of it. So this is basically the whole gist of this video. Okay, so now the second term that comes into this generative adversarial thing is adversarial. So this adversarial, if you look into the dictionary, what it says is it's basically a conflict or an opposition. So that means in this particular generative adversarial concept, there must be definitely some conflict or opposition which is going on that will be, creating some sort of, learning phase. So here, what adversarial means in terms of the picture I was trying to show you here. So you can see there is a chase going on in between the two animals. One is the cheetah, and other one is deer. So it's trying to, there is a chase going on in terms of the hunting process. So basically, can anyone tell me like what kind of adversarial thing going on over here? If you see this picture, can anyone tell like what kind of opposition is going on in this, like what variable they are trying to minimize or maximize, because somewhere or the other opposition means you are doing one way or the other. So can anyone tell that? Anyone of you? Okay, so I think no, you don't know this. Let me explain that. So what happens is, so first of all, a quick feedback. My voice is audible to all of you or not? Just wanted to have a quick feedback on that.
Yes, sir. Yes, sir.
Okay.
Yes,
So
sir. Yeah.
okay, so the thing is, the adversarial that is happening here is in terms of the distance in between these two animals. So what is the main objective of this tiger? The main objective of this tiger is to actually minimize the distance. So that is the main objective of this tiger. Whereas the what is the objective of the deer? The objective of the deer is to maximize the distance. So what is happening is there is a min max game going on with respect to the distance between them, where the maximization, what happens is the deer is actually maximizing this game, and the lion is actually making it to be, the distance to be minimized. So basically, with respect to the tiger or lion, it is actually the concept is to minimize this distance, whereas with respect to the deer, it tries to maximize the distance. So you can see when we will be discussing the generative adversarial network, you will find this particular term, min-max term, which is very important. So then this min-max is coming because of the adversarial learning that is happening in the architecture. So this is showing you a practical way of showing you a practical example of in real life, like how come like how adversarial learning happens in real time. So this is the thing. So here we have min max over the distance d. So this is basically the adversarial learning that is going on. So we have learned two words in generative adversarial network. One is generative, another one is adversarial, and now the third one is network. And I think everybody knows what networks are all about. So it's basically interconnection of the neurons, whether it's a neural network or a CNN. So the network keyword comes from there. So as far as the topic generative adversarial network is concerned, so I have discussed the three keywords that form GAN. So let us now discuss further onto this. So this is just showing you a typical its significance or the improvement in the literature work that has progressed from 2014 to 2018. This slide is old. In the latest literature, you will find more crisp and more bigger pictures. So this one is an old picture. So here you can see where in 2014, when this particular paper was proposed, at that time the quality of the image was like this. So it was not that good. But as we progressed further down the line, from 2014 to 2018, now you observe that the quality of the picture in the 2018 was much sharper, crispier, and bigger as compared to the as compared to the 2014. So this is just showing you that particular progress in the GANs. And nowadays it's like more competitive, more advancement has happened, and the quality of the images are much crispier and much better as compared to the earlier cases. Okay, so now let me change the colors here just to make it pleasant. Just a minute. Okay, so now we have discussed the two classes. First is the discriminative model class. So what it does is it discriminates between the two classes of data, and the second one is the generative model. And the second one, generative model, I will show you what this means. Like I have written about the generative model as a generative model G to be trained on training data X sampled from some distribution D is the one which gives some random distribution Z, produces a distribution D hat which is close to D according to some closeness metric. So I think these statements are quite confusing. So let us first of all understand it through the figure, so that then once you understand from the figure, then these statements will make sense to you. So what actually is happening is this. So here, if you see here, what is happening is this particular thing which I am drawing over here in the white lines. You can understand this as a contour map of the probability distribution on a 2D plane. So this is actually represented in the form of circular pattern. So what this distribution is, actually this distribution I am denoting it by D, and the points which are lying inside this distribution D is basically the samples which are capital X, let us say. So here in this case, these capital X can be the cat images which I was showing you. So the blue points here are all cat images, original cat images, and we do not know the distribution of this. So that's why this D is there, and our target is to actually calculate this D. So our target is to actually calculate this D. That is our most important job, and this is basically what generative adversarial network is good at. So objective is to calculate D. And now how will you do that? You will do that by using another architecture, which is a generator. So here this generator is represented by a block G, and it can be a neural network or a CNN depending upon your choice. So I have just represented here by these set of neurons interconnected. So it's basically a neural network. So what happens is, what you do is, for this generator you actually sample a value Z from the known distribution capital Z. So this contour plot which I have drawn here is just an arbitrary contour plot, but this distribution already. So it can be a uniform or a Gaussian distribution. So this is just an arbitrary plot of that. So what I am trying to show is all the pink dots that we have here are the random noise samples which are represented by Z. So what we are doing, we are actually taking this Z and feeding it to the generator network, which is capital G. So you know that this Z is a random variable. So when it passes through a system of which is with a transfer function capital G, so it gets transformed into G of Z. So it's a transformed random variable, and the value of that is G of Z. So now what is our target? Our target is basically to build this network, this generator network, like how to make this network in such a way that it creates this boundary which is D hat here. So right now this D hat is very, very different. So our target is to make this boundary D hat as close as possible to this D. So this is our main target. Our target is what? To make this D hat as close as possible to this D. So this is the target of generative adversarial networks, and we try to make this D hat as close as to D by doing some closeness metric, and that metric we will see when we will derive this expression. So that expression actually is basically trying to make this D close to D hat, and the metric I will just write it down here so that you can immediately correlate it with when we will be down there. So it's basically KL divergence. So if you observe the derivation of the generative adversarial network, there we have KL divergence coming into play. So this particular metric is trying to compare these two distributions D and D hat, and making them close to each other. So what happens is, generative adversarial network is trying to make this distribution as close as possible to D. So let us see how we can do that. So basically what is happening is, this is again showing you that same phenomena which I was discussing here, but I am showing you how gradually this generator is becoming smart enough so that the contour plots that we are getting here as d hat becomes refined. Each and with each and every iteration it gets refined every time, and how it is becoming more and more better as the training iterations proceed. So here you can see that with iteration 10 you have some distribution which is looking quite weird, because it's the initial stage of learning, and then as you move further with the iterations, you can see how the contour plots are getting fine and fine, and it's becoming better and better. And finally you can see after long iterations it might be the case that this particular distribution will look close as this distribution which is here d, which is unknown to us, we do not know it. So we are trying to approximate it with using this distribution. So now the important thing is basically how this learning actually takes place. So this learning takes place with the help of another block which is discriminator over here. So this discriminator actually helps in actually doing this learning process, which is going from here to here, going from here to here, and then from here to here. So this discriminator actually takes two inputs into its account. First input is coming from this side, and second input is coming from this side. And we all know that the input which is coming from this side is given by capital X equal to small x, which is the random variable instantiation of this capital X. So this is basically a real data. This is basically a real data. We all know, because this is basically the cat images in the training data set. And we all know that the generator is trying to come up with these pink dots which are inside this distribution, which is actually nothing but g of z. And what happens is these data is actually a fake data. So what happens, the discriminator is trying to work as a discriminative model. So we have discussed this discriminative model also in our earlier slide. So what is happening, this discriminator is acting as a discriminative model which tries to distinguish between the real data as well as from the fake data. So in doing that decision, if it creates no loss, let us say the loss is 0, let us say. So if it creates no loss, that means your generator is smart enough to produce g of z which are actually looking quite similar to the real data. That's why the loss incurring is 0. But if the loss value is very high, then what will happen is, it means that our discriminator is very smart and it can still detect that this g of z is a fake data and this is a real data. So our generator is not able to produce the samples that good enough, and that's why our loss is very high. So if our loss is very high, then what will happen is this loss will be taken into account to do the back propagation, and that back propagation will actually will be used to train the discriminator as well as the generator. So this loss will actually play a role in training the discriminator and generator during the training process, so that both of them will become intelligent enough to do this task. So you will see in the coming slides that when the loss incurred by the discriminator, if it is value is 0.5, at that point what happens is the generator is completely confused whether it is coming from, whether the data coming from the real is real or from the fake is real. So in that situation, when the value is 0.5, generator becomes very smart enough to generate fake data which looks exactly as the real data. So this is actually the value of 0.5 you can derive also. I will show you how to do that. So that value is the exact value where the generator has learned to generate artificial data. So here again it is showing you that same story. Instead of cat images we have MNIST dataset image. So here what we are doing is we are taking a sample of this, which is a real sample, and from here you are taking a random noise, and you can see how this noise having a vector of 100 cross 1 is actually expanded into a 28 cross 28 vector of output nodes which are actually reshaped back into an image. So this is basically a 28 cross 28. So you can see how this particular generative network is like, a expanded network where the input is very small depending upon the dimension of the sample that you are taking, and the output is basically the 28 cross 28 neurons, which you are actually reshaping it into the form of an image. And why we are doing a reshaping? Because we are using neural networks here. So if you use CNN, there is no point in doing it. But for this particular case, this is the thing. So here you have a fake sample. So what is happening is, again, a generator, our discriminator is again a neural network, and it tries to find out the difference between the real and the fake sample. So this is just again the same story repeated in terms of the MNIST dataset. Okay, so the learning mechanism that we have in case of generative adversarial network is that first of all you have to train the discriminator first. So when you train the discriminator, in that situation, what happens is you feed the random vector Z into the generator. Then the generator will actually generate some artificial instance of the MNIST data set, let us say, and you attach a label of y equal to 0 with that. And then you already know from the real data set, you will attach y equal to 1 for these images. And now you will only train the discriminator. You will only train the discriminator, and discriminator will be, you will make this discriminator learn whether this is a real, this is the fake data and this is the real data. So in the training of the discriminator, generator is fixed, it's not trained, and discriminator is trained. So this is training of the discriminator. And once this is done, then what happens is you have training of the generator phase. So in training of the generator phase, what happens is our discriminator is somewhat smart now. So it can judge like whether the data coming from the real is real and from the fake is fake. So now what happens is, when you want to train the generator, train in the sense you have to adjust the weights and bias of the generator. So what happens now is, when this generator is generating an image, you artificially append y equal to 1 in that case. So this is very important step, because you know that this particular image is a fake image. So let's try to judge discriminator whether it can judge this particular image as real image or a fake image. So we are providing an adversarial example to this discriminator by ourselves giving y equal to 1 to this image instead of y equal to 0. So now we think that discriminator is smart enough. It should, distinguish that, bro, no, this label y equal to 1 is not true. It has to be y equal to 0. But it might be the case that discriminator will not be able to distinguish this particular image with y equal to 1 as the true label. So it might be the case that it will create an error with this. So whatever error that is generated in this situation will be back propagated to adjust the weights of generator. So in this situation, discriminator will not be trained. It will be fixed. So it will not be trained, only the generator will be trained. So this is basically, and then you keep on repeating these exercises. Like once you have done it for one epoch, then you again, do this same process again and again and again. So for a very few number of steps, once we finish that off, the discriminator and the generator will be trained properly, and then you can disconnect this discriminator, then you can disconnect this discriminator, and then you will have only generator, which actually generates new data set for you. So it will be your generative network. Okay, so now the important part is the loss function that is involved in this generative adversarial network. So the loss function, so before going there, I just wanted to give you a small terminology, like because you will see this in the loss function. So what this is basically is like, this is the probability distribution Pz of z, which is known to you. So we are representing it by this, and then we have a generator G, which takes, we have two arguments with this. One is this double dot, which means you are actually putting this sample into this, and we have theta G, which is actually the trainable parameters of this G, which has to be adjusted during the training process. So this is the generator, and then you have, G of Z. So this is already discussed that it's a transformed random variable. So all these data points which are inside will be represented by G of Z. And this contour which you are generating by the generator is represented by Pg of G of Z. And it's also simple because all the points which are lying inside this Pg, which is the generator probability distribution. So inside that argument, you have this. And our target is to make this equal to the P data of X, which is the original distribution which we have over here. So this is what our objective is. And this is the discriminator. And in this discriminator also, we have this double dot, means images are coming from here also, and images are coming from here also into this particular input. And this theta d is the weights and biases of this discriminator which has to be adjusted. So this is basically the weights and bias for this particular discriminator. And output of this discriminator will be two. One is d of x. What is this d of x? It's basically the random variable x which is going inside this discriminator, and it's modified as d of x. And another one is d of g of z. And why this is the thing? Because you are actually feeding this g of z again into this discriminator d. So it is also modified like this. And these values will be in between 0 and 1 because you are actually looking for the probabilities which are not beyond 0 and 1. So this is the convention that I will be using while deriving the loss function. So I'll be a little bit quick on this. So this is basically the terminology you should keep in mind. So the loss function, so what I will be doing now is I will be deriving the generative adversarial loss function from scratch. So you look onto this, and then we'll go further. So this is basically the binary cross entropy, which I think most of the people know. So we will derive the loss function for the generative adversarial network from scratch. So this already, I think most of the people who understood or gone through machine learning course must be knowing this. So it's a binary cross entropy. So now the important thing is, if we are considering the discriminator training, in the case of discriminator training, the data that is coming from P data of X, which is the original distribution, in that case, the labels corresponding to that is y equal to 1. We all know that because this is the real data, this is the real distribution, and whatever labels that are there with that distribution, we are putting it as y equal to 1. So the output y hat, which is generated by this particular thing, this is basically what we are talking about, d of x. So the output is generated by this thing is d of x, because you are feeding the original input into the discriminative model. So it's d of x. So now if you put this y hat, which is the resultant output, and the y which is equal to 1 into this expression, which is the binary cross entropy 1, then you will get this expression. So this is the first expression that you have now with respect to the discriminator training. And now what happens now? If the data is coming from the generator, then you know that the data that is coming from the generator is fake. So the y equal to 0 will be there with that. So in the discriminative training, y equal to 0 you are providing, that is the label, and the estimated value of y hat, which is coming out of the discriminator, is d of g of z. Because you know here, this is d of g of z, it's coming from the generator side, and you know that, and if you put this y hat and y equal to 0 into the binary cross entropy function here, you will get log of 1 minus d of g of z. So there are two terms now. One is log of d of x, and the another term is log of 1 minus d of g of z. So these two terms, what we are trying to do now is we are trying to play with them. So now if you consider the discriminator, if you consider the discriminator ideal discriminator, like what kind of discriminator is ideal? In that situation, in case of ideal discriminator, you want the data which is coming from the real sample space. When d is operated on that, it should be 1. Like you want that if the image is real, then the discriminator should give you a value of 1. That is quite simple, and I think everybody will agree with that, that this decision is what actually an ideal discriminator should look like. And in case of fake data, which is g of z, if you operate d on that, the discriminator should immediately reject it. It should say that it's a fake data, and the value should come out to be 0. So that is also, I think, quite evident from there is nothing fancy about this. So it's quite easy to understand this particular objective of the ideal discriminator. So what we are trying to do now is we are actually trying to combine these two together, this term and this term, and let us see what will happen. So our objective. So the important thing is we want this, from the ideal discriminator. So let us see how we can get these objectives out of from this and this term. So what we are doing now is we are actually using these two terms, and we added these two terms which we have just derived, and we operated a max on this, and we are saying let's maximize this argument with respect to D. So this is what we are actually trying to do, and our main target is, if we do this, are we getting this as an final answer? That is our main objective. So again, I'll repeat, if I'm maximizing this, are we getting this as our final answer or not? So here, let us see whether we are able to achieve that or not. So if you see this particular log d of x and log of 1 minus d of g of z, I am separately plotting these curves. So this is basically log of d of x, and this is log of 1 minus d of g of z curve. So note that we are restricting our values from 0 to 1, and we are not going outside 1 because this is a probability. So we cannot go beyond 1. So we have to restrict ourselves in between 0 and 1. So this is gone. So we do not want to focus beyond 1. So this is there. So now what happens is, what we are saying is we want to maximize the stuff, which is maximize the D. So if you want to maximize D, what is happening is, somewhere or the other, you are actually trying to come on this curve and trying to find out the maximum value of this. That is what this is all about. So what happens now, if you come on this curve and trying to see the maximum point, obviously this is the maximum point here, and this maximum point actually corresponds to what? It corresponds to d of x equal to 1. Similarly, if you look here on the other side, that is log of 1 minus d of g of z, this curve looks like this. And again, if you want to do a maximization, if you want to find the maximum of this curve, then you can see the maximum value will be this one. This is the maximum value. And at this point, what is the answer? Our answer is d of g of z equal to 0. So ultimately, we started off with the objective that our d of x here has to be 1 and d of g of z has to be 0, and we were thinking, can we achieve this target by maximizing onto this argument? Can we do that? So yeah, it is possible. As you can see here, if you do a maximization on both of these curves, you will get these values which you were trying to achieve from the ideal discriminator. So here, if you do a maximization on this argument, you will get the ideal value of the discriminator. Now, from the generator point of view, because generator is also there. So for generator point of view, what you want from the generator? You want that whatever samples you are taking from the generator, that is g of z, if it passes to the discriminator should not be able to detect it as a fake image. So if it is not able to detect it as a fake image, means it will detect it as a real image. So that's why we are writing it as 1 here. So you can see the main objective of the generator is to create an image g of z in such a way that when you operate d on that image g of z, it should fail and it should give a value of 1 instead of 0. So again, our objective is to make this as 1. And now if you look at this function, there is only one term which involves g, this one. There is no term involving g here. So what we will do is we will discard this and we will focus on this term. So what we are now saying is, if we do minimization operation on this log of 1 minus d of g of z, are we able to get this particular objective 1 equal to 1 or not? This is our again same question. So now this curve is similar to this curve which we have already discussed here. This is the log of 1 minus d of g of x. So you can see now that if you minimize, g, that means you are somewhere here in this point. So we are not hitting to the situation where things are infinite, we are getting close to it, but not to the infinite sense. So somewhere or the other, you are here so that you are not exactly one, because otherwise problems will be there because of the log. So we are somewhere close to it. So here you can see, if you find the value, so this value will be d of g of z equal to 1. So that means if you do a minimization on this, then you will be able to achieve the target of d of g of z as 1. So that is again important. So just a quick feedback, and my voice is audible to everyone?
Yes, sir.
Okay, okay. So this objective is also met once you do a minimization operation on log of 1 minus d of g of z. So now what is happening? Now what we will do is we will do min max. So now this term must be quite familiar to do you, because this is the famous term that you have for generative adversarial networks, where you have these two terms, and then you have minimization with respect to g and maximization with respect to d. So if you do maximization with respect to d, these two terms will be there, and if you do minimization with respect to g, only this term will be there. So this is somewhere or the other the the objective function of GAN, but we are not close to what's written in the paper, and the exact expression for that is this. So let me erase this. So the exact expression is this. And here what we have is we have extra terms, which is the expectation operator here, and again we have another expectation operator this side. So what is happening is, it's like you are actually sampling this x from p data of x. So this is basically this is just showing you that you are sampling x from p data of x, and that x is fed into this, and you are sampling z from p z of z, which is already a known distribution. So this is just representing that. And why this expectation is coming? Because now you are actually considering multiple images in the data set and not the single image. So here this particular expression was valid for only single image, which we were actually discussing for our case. But if there are multiple such images, so you have to use the expectation to get to the final answer. So this is basically the final objective function of GAN. So this is the one which actually you will see in most of the GAN literature. And the important point is, like, I don't want to go into details of this derivation, but this is basically because of the time limit, because we are already left with 10 minutes. So here you can see this is the algorithm that we have in case of the generative adversarial networks. So what you do is you actually sample the noise from the noise vector, and then you sample the m examples from the actual distribution, which p data of x, which you do not know, and then you do a ascending in the stochastic gradient by taking the derivative with respect to theta d of this objective function here. So this is nothing but the objective function we have just discussed, and this is basically the approximation of the expectation operator that you can do by writing 1 upon m sigma I running from 1 to m. So you are doing a derivative with respect to the generator here to calculate the gradients, and then once you do the training of the discriminator here, then you move to generator, where you again do the stochastic gradient descent to update the gradients of the generator. So this is basically a quite famous, you can see this in the paper, like this particular algorithm, how to update it. And again, the loss function that we have here, which I was just discussing in the earlier slide, what happens is, the best discriminator that you can obtain, you can derive this. I will show you the slide, but this derivation here will give you the optimal discriminator, which is the best discriminator. So here, if you see, our objective is to make PG equal to P data of X. That is our main objective. That is, the generator probability distribution should be same as the actual data distribution. So if you put this value here in this expression, you will get a value of 0.5. So this is what I was telling you, that the optimal discriminator, when it gives a value of 0.5, means your generator is successful in generating images which are as close as to the real images, and the distribution PG will exactly match the actual unknown distribution P data of X. So this is basically the um, 0.5, which is the final answer for doing this. I'm not going into the details of these derivations because these derivations are trying to solidify these concepts, but time is not there for this. But I will give you the reference like from where you can understand all this in detail. So this is basically trying to show you the derivation for how you get this optimal discriminator DG star. So just for your understanding, I will show you the link from where you can watch this in more detail. So let me show you that. So here I have some lectures which I have recorded out for our class. So you can watch it from here. You can search my name and then you can see all the details regarding this. Like so, all this discussion which I was telling you, all this will be discussed in detail here. So you can watch it from here. So so this was just showing you a bit of theory and how to derive this optimal discriminator in a quick way because of the time limits. So
Sir,
again,
share the
I
link.
think, sorry.
Sir, share the YouTube link.
Okay, just a second then. So this is the link. So you can watch from here and see like the details about how this all derivation and everything is going on. And so everything is basically in details like how we are doing all this stuff. So I don't want to go into details of this. So yeah, once we find the value of optimal generator, so you can see here the optimal generator that you will obtain is basically some KL divergence will come into the derivation. So this is important, like we have a KL divergence. KL divergence basically is a metric which actually tries to find out how close the two probability distributions are to each other. So it tries to find out that whether this distribution, if this is close to this or not. So if it is completely different, KL will be different. If it is close, then KL will have some other value. So KL divergence actually tries to find out how close it is. So once you try to minimize the G, then what happens is like for example, this is the final answer that you will get. So here, if you minimize the G, that means in this expression, the only way to minimize G will be that this particular term should go away. This particular term should go to 0 because it is minus log 4, which is a constant, so it cannot go to 0. The only way this particular thing can go to 0 is that this particular term will be 0. So this is JSD is nothing but it's a Janssen-Shannon divergence. So again, this is nothing but it's a way of actually adding these two KL divergence together to form Jensen's Shannon divergence. So the formula for that I have written somewhere, I think down the I think so. I don't know here whether it's there or not. No, it's not there. But you can watch the videos where we are actually trying to represent these two KL divergences together and club them into single expression, which is the Jensen-Shannon divergence. So if you want to come up with the optimal generator, so you want to minimize this expression. So if you want to minimize this expression, the only way to do that is to make this equal to 0. So this is equal to 0 only if you see it will only be happening when your P of G of X will be equal to P data of X. So you can check that out. So in this way, you can get the optimal value of the generator, where your value of that optimal generator will be minus log 4, and it is achieved when you get this as the answer. So this actually finishes off with the concept of generative adversarial network. So I'm done. So if anyone has any question, they can ask things.
Professor Alad, can I request you to write your mail ID so that others can follow it up?
Okay.
If they have any question, they can write to you.
Yeah. I'll write it down. So
And for the candidates, I am
yes,
getting a query in the chat box saying that you have not received the folder. I have shared a folder with all of you, and that message must have gone to you from Google only. Please check your mailbox. In the mail ID what you have mentioned, I have sent him to the same mail ID. So we'll have to check in that mail ID, that folder which has been shared. And if you go to the folder, you get all the references, the video recording, schedule, everything. What I do is that for your convenience, I will send once more the schedule to all of you today. So that you can see that what is tomorrow, day after tomorrow, etc. All the programs you can see there. Yeah, I suppose Professor Allad has already mentioned his mail ID. You can write to him, and then anything else is there, we can discuss afterwards. So this is all for today.
So
Tomorrow
yeah,
at
it's
same
there.
time, 5 o'clock we
I
will be
already
meeting.
forwarded him. So all already forwarded. So in case.
Okay. I suppose we can close it, Professor Allad?
Yes.
We can close it?
Close. Yeah.
Okay. Thank you.
Yes.
Thank you very much.
Yeah. Thank you. Sir.
Bye.
Thank you.
Bye.
Thank you.